Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. In this particular lecture, we want to focus on the energy eigenvalues that come out of the radial Schrödinger's equation. And we want to, in particular, enumerate the allowed energy states that the electron can have when it's bound to a proton to form this hydrogen atom. So this is sort of it's a classic. I mean, it's a time-honored discussion of that occurs in all quantum mechanics courses. The energy eigenvalues are the sorts of things that you can easily measure experimentally. So you're always using the predictions of these theories to compare against experiments. So it's an important topic for that reason. By way of summary, let me just say that the radial Schrödinger equation that we discussed in the last lecture, I write it down here just to remind you what it looked like. And these energy eigenvalues, there's only going to be certain energies E that satisfy this differential equation for particular values of script L. And what we're trying to do is we're trying to come up with an understanding of what the allowed energies are, right? What the allowed energies are, given the fact that these energy eigenvalues are known, right? They're known from Laguerre's discussion of that radial differential equation. So to motivate this, I'd like to just show you how the argument goes. I'll pick a very simple case because I can work through it pretty quickly. More complicated cases can be worked through following the same logic. But in order for you to understand how these energy eigenvalues come out, let's just consider the case when script L, right? This quantum number script L is equal to 0. And that implies that the principal quantum number n is equal to unity because script L is always going to be a number less than n, right? The reason I pick script L equal to 0 is because this term here then disappears, right? And we're left with a much simpler differential equation to deal with, right? So once these two quantum numbers are specified, then the eigenfunction for the radial differential equation, capital R, can be indexed appropriately. It's indexed by the numbers n and l. And you can then look up what the form of this function is, right? The table that I gave in the previous slide will allow you to immediately know what the solution is, right? And I just copy the solution down. The solution is a constant A times this exponential e to the minus r over a0, where a0 is some parameter that sets the length scale for the hydrogen atom. It turns out it's gonna specify the radius of the ground state orbit for the electron in the hydrogen atom. But at this point, we don't know what a0 is. It's just some constant. And what we're going to try and do is determine both a0, right, and also the energy eigenvalue E1 for this quantum state n equals to 1. So how do you do this? Well, I've got a solution, right? And so if this solution is correct, I should be able to plug it back into this differential equation, and I can see what conditions result given that proposed solution. So that's exactly what I do in this slide. You have to take two derivatives of the radial eigenfunction capital R. You have to take two derivatives with respect to the coordinate small r. Right? There's a few lines of algebra that you have to go through. But at the end of the day, right, you're left with an equation that looks like this. And you can check my arithmetic, right, to make sure that you understand how you get to this point. But this equation is kind of interesting in itself because it says there's some group of numbers, some group of complicated numbers multiplied by the radial position vector r, plus another group of constants, and that has got to be equal to 0. And that equation has to be true for any value of r that specifies the electron position as the electron moves around this hydrogen atom. Well, that's hard to accomplish, right? You can imagine that maybe you can solve this equation for one value of r, but the fact that it has to be true for all values of r imposes a condition which says that the only way it can be true is if both the coefficients in parentheses, right, are equal to 0 always, right? They're identically equal to 0. If they were not, it would be virtually impossible to satisfy this equation for any value of the coordinate r that you could imagine. So we use that fact to take this one equation and split it into two separate equations, right? And these two equations are labeled 1 and 2 in this slide, right? It's basically saying that those quantities in parentheses are both equal to 0 simultaneously, right? The first equation, to be true, gives us an expression for the energy eigenvalue E sub 1. And that energy eigenvalue is h bar squared over 2 times the mass of the electron times this parameter 1 over A0 squared, which we have to determine. And that parameter 1 over A0 squared, we can get an expression for A0 by looking at equation 2 here. So if we solve equation 2 for A0, right, we've got this complicated expression which can be rewritten in a number of different ways. It's interesting that A0 only depends on fundamental constants in nature. It depends on this dielectric, it depends on the permittivity of vacuum. That's this quantity epsilon naught that surfaces when we discuss Coulomb's law. It's got Planck's constant squared. It's got the mass of the electron. It's got the charge on the electron squared. So this parameter A0 is basically determined by a lot of constants of nature, right? Things that we don't really have control over. And there are many ways to write A0. The way I like to write it is in terms of the Compton wavelength, which is a quantity that we discussed in the first week of the course. That's just h over m times c, where m is now the mass of the electron. There's a factor of 1 over 2 pi, and there's this constant 1 over alpha that is defined down here. So alpha is this group of constants. Turns out alpha is equal to 1 over 137. And so when you put that value in, use the Compton wavelength, which we discussed earlier in the semester, you find out that this constant A0 is 52.9 picometers. And that is an important number, right? That basically is telling you the radius of the hydrogen atom. It's basically telling you that the wave function, the radial wave function, drops to 1 over E when R is equal to A0. And so A0 is 52.9 picometers, and that basically defines the radius of the first energy eigenstate of the hydrogen atom. Okay, number of things to realize, again, I just come back to this value for the Compton wavelength. That was 2.4 picometers, right? That figures into the calculation for the radius of this lowest energy orbit, A0. For those of you that remember the first week of lectures, right, this value for the first quantum radius in Bohr's model also was precisely equal to 52.9 picometers. So, right, the radius of Bohr's first circular orbit for the electron in the hydrogen atom, that value is actually recovered from Schrödinger's equation, right? It's one of the hallmarks of quantum mechanics that this value is reproduced from this very complicated set of differential equations. And of course, I wouldn't be up here talking about it if the experiment didn't match theory very well. So experimentally, if you go in and you measure the radius of that first quantum orbit, you get this number 52.9 picometers, which is predicted by Schrödinger's equation. Truly a remarkable result. Once you have an expression for A0, then you can go back and evaluate this equation 1 and calculate what the energy eigenvalue is, right? So that's just going to be E1, and it's going to involve an expression for A0. I just multiply, I get rid of A0 squared because I want to express the energy eigenvalue E1 in terms of fundamental constants. So this is just a bit of arithmetic here. This whole quantity here is basically just unity, right? And at the end of the day, I got an expression for the energy eigenvalue of the lowest energy state in the hydrogen atom is just equal to -1/2 times the mass on the electron times C times this constant alpha quantity squared. All right? All fundamental constants in nature here, right? C is the speed of light, m is the mass of the electron, and I just evaluate this expression here, find out that the allowed energy eigenvalue is -2.18 times 10 to the -18 joules. I can convert that 2.18, 10 to the -18 joules, I can convert that to electron volts, and I get -13.6 electron volts. So again, this number exactly matches the energy eigenvalues, or matches the allowed energies that Bohr specified for his solution of the hydrogen atom problem back in the early 1900s, and that was a semi-classical treatment. You get the exact same number following this discussion from Schrödinger's equation, which again to me is a truly remarkable result. This is the case for the ground state energy. This is the lowest energy state for the electron and hydrogen. So if you just put the electron close to a proton, let those two entities form a hydrogen atom, the electron would have -13.6 electron volts worth of energy with respect to the case when the proton and the electron are infinitely far apart. All right, so the minus number always refers to our zero of energy, and our zero of energy is always the case when these two guys are far apart from one another. In general, you can work through this discussion for any energy eigenvalue, and in the math notes in lecture 5.05, there's an equation buried in there that allows you to solve for the various energy eigenvalues E sub n. They're all indexed by this quantum number n, and quantum number n is an integer value. It's positive, 1, 2, 3, 4, so on and so forth. So you can solve this equation for E sub n, and at the end of the day, you get this very familiar equation, which again matches Bohr's theory. The allowed energy eigenvalues E sub n are -13.6 eV divided by n squared, where n is a quantum number. So what I'll say is that Schrödinger's equation precisely matches Bohr's theory only for one case, and that's when the quantum number n is equal to 1 and the quantum number L, script L, is equal to 0. In general, for any other values of quantum numbers, there's going to be subtle differences between Schrödinger's and Bohr's theory. Schrödinger's theory is much more accurate. All these predictions that we're going to discuss in the next few days, next few lectures, all these predictions have been borne out very, very nicely by experimental results. So Schrödinger's equation, in fact, does nail the problem very, very precisely, very exactly. It's probably useful just to summarize where we're at, okay, what we've achieved. And basically what we have achieved is we've achieved a way to specify the eigenfunctions that satisfy Schrödinger's equation. These eigenfunctions are a product of the spherical harmonics, capital Y, There's two quantum numbers, L and M, that you have to specify in order to select out the correct value of Y for a particular quantum state. The wave function in theta and phi direction have to be multiplied by the wave function capital R in the radial direction. And to specify the radial wave function, you've got to know the quantum numbers N and L. So this table attempts to summarize the values of N, script L, and M that are allowed. And I just sequentially run through the principal quantum numbers, 1, 2, 3. I list the values of script L that are consistent with the particular choice of N. And then I also list the values of small m that are consistent with the different values for script L. And this chart opens up or illustrates some interesting differences between Bohr's model and Schrödinger's model. And one of those differences is referred to as the degeneracy of each quantum state. So what I will say is, I will say that since the energy of the state depends on the principal quantum number n, all the states, for instance, in one row of this table, all those states have precisely the same energy. But for each combination of quantum numbers, you actually have a different quantum state. And that's something we have to discuss later on. We'll do that next week. But it basically is telling you that these different energy levels are degenerate, which means there are many ways many quantum states that you can put an electron into and still have the same energy eigenvalue, E sub n. So I just list the degeneracy as a function of the principal quantum number n here, just to give you a sense of this new feature. That this was not something that Bohr's model predicted, but it's an inherent prediction that comes out of Schrödinger. What you can do now is you can start to map out these energy levels, right? So here's the ground state level, n equals 1, it's minus 13.6 eV below the vacuum level, which is up here at E equals 0, right? The quantum numbers that describe the electron when it's in this energy level, those quantum numbers are n equals 1, script L equals 0, script M is equal to 0. The first excited state corresponds to the n equals 2 quantum number. But when you put n equals 2 in the formula that I gave in the previous slide, you'll find out this energy eigenvalue is at minus 3.4 eV, right? This again matches what Bohr predicted, but what Bohr did not predict was these other states that are possible, right? And so you can see that there are four different quantum states that correspond to the different combinations script L and script M that can be described, that all have the same energy as minus 3.4. You know, you can continue this discussion. So I list the results for n equals 3. Now we've got 9 different quantum states that can be accommodated at the same energy value. This degeneracy is a new idea, and it's really a simple way to learn something about a complicated system. So what I always like to do is I like to try and explain it by saying, let's say we have some system of particles, right? And let's say you can magically go in there and you can grab one of the particles and measure the energy that that particle has. So in this case, these green balls would represent hydrogen atoms, and all the hydrogen atoms are, let's say, in some different energy states. So you just go grab one of the hydrogen atoms and you measure the energy that the electron has in that hydrogen atom. And depending on what energy it has, you put that atom in a bin, right, for different energies, different energy eigenvalues. So we know the energy eigenvalues are E1, E2, E3, E4, right? Each time we pick a hydrogen atom out, we measure its energy somehow, and then we sort that hydrogen atom into the appropriate bin, right? So one outcome of this experiment is that all bins are roughly equally filled, right? And that would simply mean that the probability of finding a hydrogen atom with a particular energy, E2, E3, E4, right? The probability is uniform, right? There's no strong dependence on energy for the hydrogen atoms. That's one scenario. Another scenario might be that one energy is particularly favored, right? So in this simple example, I just select out the bin with energy E2, and after, let's say, 10 or so experiments, you find that there's a large number of atoms that start to accumulate in that bin labeled E2. That means something, right? It just simply means that there are more ways in this collection of atoms. Right? There are more ways for the the hydrogen atom, to have energy E2 than all the other energies that are available. So that indicates some sort of internal structure for this hydrogen atom, and it's an indirect reflection of the degeneracy. It just means that there are more ways to form a hydrogen atom with a particular energy E2 than there might be for these other energy states. So it's a very qualitative way to think about degeneracy, but it's an indication that something's going on. It's not as obvious as you might first expect. So we'll come back to the degeneracy later on in the semester. It turns out it's a real big deal, and we have to properly take it into account when we start to do detailed calculations. So I just want you to start thinking about this concept, because it's not something that you often find in classical physics. I can continue this discussion, right? So for example, I can discuss the n=2 quantum state for the hydrogen atom. I can write down the wave functions for these various allowed energy states. I can calculate what the allowed energy state is for the n=2 state. It's going to turn out to be minus 3.4 eV. And I can actually, knowing the quantum numbers, n, L, and m, I can now actually explicitly write down what these wave functions are. And once I know n, L, and m, I can go to those tables that I gave in the previous lecture, and I can get analytical forms for capital R, the wave function in the radial direction, and capital Y, the appropriate wave function in the theta and phi direction. So these things are now all possible once we have these solutions tabulated for Schrödinger's equation. I will also say that different disciplines have developed different ways to specify these quantum numbers. And in particular, the chemists have developed a specific code that takes the quantum number script L and converts it into a letter. So the code is given in this table, and depending on what the value for script L is, the chemists tend to refer to electrons in the L=0 state as S electrons. They refer to electrons in the L=1 state as P electrons. When L is equal to 2, those are referred to as D electrons. And you can start now to write down explicitly the wave functions for electrons in each of these energy levels. All of these energy levels are degenerate because they all have the same value for n. In this case, n is equal to 2, right? There are some subtleties involved in the wave functions. I just mentioned that very often in the chemistry literature, these wave functions are combined to form molecular orbitals. I don't want to spend a whole lot of time talking about that right now, but basically, two of these angular functions are complex, so they have real and imaginary parts. Sometimes that's difficult to deal with mathematically, so what a lot of people do is they'll rewrite these wave functions with imaginary components, by linearly combining or linearly subtracting the two wave functions to eliminate the imaginary term. And when they do that, they form what are referred to as orbitals or molecular orbitals. So you'll see that that nomenclature in the literature a lot. And there's a discussion here that if you're interested in those issues, you can read it. I try to explain it in some detail. We can go to the n equals 3 quantum state. Now we've got nine separate states that are all equal in energy. These states, again, have a range of quantum numbers, and you have to be able to list those quantum numbers in a systematic way. Once you know the quantum numbers, you can then specify the appropriate wave functions. You can look up these wave functions in those tables, and so you know exactly what the wave function is for an electron in any one of these quantum states. It's useful to visualize the solutions of Schrödinger's equation rather than just looking at the equation itself. And I'll just mention there are many ways to do this. If you look at the older textbooks, the drawings for the wave functions were rather obscure, right? They were based on actually evaluating the wave functions in detail and devising techniques to plot where the electron is likely to be and at what radius the electron is most likely to be, depending on which quantum state it's in. And so you get these dot matrix plots where dark indicates high probability of finding an electron and light represents low probability of finding an electron. These plots were fashionable up until the, I would say 1960s, early 1970s. At that point in time, computers started to develop an ability to visualize these wave functions in 3 dimensions. So you started to get plots that look like this. These plots are representing the probability density that you find in an electron at different radii for different values of theta and phi for the appropriate quantum numbers that are indicated by each figure. And of course, nowadays you've got the web, and so you've got an amazing ability to visualize these wave functions. And I just list some very nice plots that I found, and I give the website, so you're free to take a look at these things in detail. What these geometric patterns represent is they represent the probability that you find an electron at a particular distance, a particular radial distance, away from a hydrogen atom, or away from the nucleus in the hydrogen atom. White represents high probability. Black or dark represents a very low probability density. So there's these wave functions that we listed, right? These wave functions that we listed here, when they're properly analyzed and plotted, give rise to these very complicated plots. And these plots are then used to explain an awful lot in chemistry and in condensed matter physics. Right? They form the basis for a huge understanding of physics and chemistry at the atomic length scale. So if you like to look at these types of plots, in the appendix of this lecture, I give about a half a dozen wave sites that emphasize different aspects of these wave functions, and I encourage you to go take a look at them if you have the time and interest. What I will say is, in the next set of lectures that we're going to work on, we're going to investigate what these plots actually represent. We'll do some detailed calculations. We'll start to work out some specific problems using these wave functions, and try to convince you that once you know the wave functions, you know everything there is you need to know about the electron in the hydrogen atom. And we'll go through some specific examples, so it won't be so much theoretical discussion. It'll be actually practically using the wave functions to generate diagrams or plots that look like this. So that'll be the topic of the next 4 or 5 lectures, and stay tuned as we develop those, and we'll be presenting them in next week's lectures. So thanks a lot to think about here. So you have to work at this if you want to understand it, and come on back next week, because we'll be working out examples to try to illustrate a lot of the concepts that we've just developed.